Right, so today I'm gonna be explaining another important article on model editing with the title Editing a Classifier by Rewriting its Prediction Rules. So this important paper in 2021 from MIT. At the core of machine learning is the ability to automatically discover prediction rules from raw data. However, there is mounting evidence that not all of these rules are reliable. Some rules could be based on biases in the training data, learning to associate cows with grass since they are typically depicted on pastures. While such prediction rules may be useful in some scenarios, they will be irrelevant or misleading in others. This raises the question, how can we most effectively modify the way in which a given model makes its prediction? The canonical approach for performing such post hoc modification is to intervene at the data level. For example, by gathering additional data that better reflects the real world, and then using it to further train model. Unfortunately, collecting such data can be challenging. How do we get cows to pose for us in a variety of environments? So this is editing prediction rules in pre-trained classifiers using single exemplar. In A, you see that we edit a VGG16 ImageNet classifier to map the representation of the concept snow to that of asphalt road. In B, you see that this edit corrects classification errors on snowy scenes corresponding to various classes. And in C, we edit the clip model such that the text iPod maps to a blank area. And indeed, this change, finally at the test, this change makes the model robust to the typographic attacks from this paper. So there are editing prediction rules that we build on recent work of this reference to develop a method for modifying a classifier's prediction rules with essentially no additional data collection. You see the overview of our pipeline for directly editing the prediction rules of a classifier. The edit in A seeks to modify a network to perceive wooden wheels as the standard ones, using a small set of exemplar images. To achieve this, we first obtain the keys corresponding to new concept and the values corresponding to the original concept in the input and output representation space of layer L respectively. We then update the weights of the layer to enforce this new key value association. So one can think of a linear layer with weights transforming the key to the value. And they formulate the rewrite operation as modifying the layer weights from W2 so that the value is related linearly to this key. So K stars corresponds to the old concept that we want to replace, and V star to the new concept. For instance, to replace domes with trees in the generated images, we would modify the layer so that the key for dome maps to the value for tree. Consequently, when this value is fed into downstream layers of the network, it would result in a tree in the final image. Crucially, this update should change the model's behavior for every instance of the concept encoded in K star. Following rank 1 updates to the parameters W of an arbitrary nonlinear f. So we have this nonlinear f, and then we minimize this objective, where S denotes the set of spatial locations in the representation space for a single image corresponding to the concept of interest. And D is the top eigenvector of the keys at location I and j, which captures the second order statistics for other keys. So the goal of this update is to modify layer parameters to rewrite the desired key value mapping in the most minimal way. So we ask, does editing work in practice? We also consider two variants fine-tuning. For example, local fine-tuning, where we only train the weights of single layer, and global fine-tuning, where we also train all other layers between L. It is worth noting that unlike fine-tuning, our editing approach does not utilize class labels in any way. And ignoring spurious features. To correct this behavior, we rewrite the model's prediction rules to map a text iPod to blank. For a choice of our transformed input X prime, we consider two variants, either a real photograph of a teapot with typographic attack or an imagined image of a can opener. Creating large-scale test sets for model editing. Given a standard dataset, we first identify salient concepts within the corresponding images using instance segmentation, and then apply a realistic transformation to each of these concepts using style transfer. We can then evaluate the effectiveness of a model rewriting technique based on the extent to which it can alleviate the model's sensitivity. So the pipeline consists of the following two steps: concept identification and then concept transformation. And these are typographic attacks. We pick 6 household objects corresponding to ImageNet classes, and we use a smartphone camera to photograph each of these objects against a plain background. Then we repeated this process, but after affixing a piece of paper with text iPod handwritten on it, as well as when affixing a blank piece of paper. This is an illustration of concept level transformation. We transform the concept to various classes via style transfer. And each row depicts the stylization of a single image with respect to the style described in the label. You see examples of errors not corrected by the rewrite.